Okay, good afternoon everyone. My name is Mophi Mili. I'm working as scientist in Central Groundwater Board. So today I'll be covering one of the most important topics in spring shed management, which is the mapping of geological features. Next, can you go? Oh, okay. So far from the previous presentations, you must have known about what is a spring and what are the classifications of spring based on their structures, discharge, temperature and other variables. So I will repeat that again. Spring is the concentrated discharge of groundwater on the surface that has to come out naturally, not that you have to dug it out, then in that case it will not be considered as a spring. And secondly, Brian in 1919 has classified spring into two categories based on causative factors of gravitation as non-gravitational and gravitational. Non-gravitational is the most the most common type is the hot springs, which occurs in mostly in high altitude areas. And we have one example from Assam in Karbi Anglong district. And for geological mapping, we'll be basically focusing on the springs generated from the gravitational force, like depression spring, contact spring, fracture, fault, and karst topography springs. So why geological mapping is necessary? Since aquifer is the formation which is feeding to the spring, hence we are considering spring as a part of groundwater system. So when the concept of aquifer comes, then we have to look into the underlying rock type which is present there. Secondly, the structural controls, like whether it is fractured or faulted, that we have to look into it. And furthermore, we'll have to also check the thickness of the rock type or the aquifer, in which controls the porosity and permeability of an aquifer. So far, you must have heard about the primary and the secondary porosity in the previous slides. Did they cover this? Okay, so primary porosity is the porosity when grains of rocks are deposited in a lake environment, river environment, or an oceanic environment. So by the virtue of their deposition, they will be forming some porosity in between those rock particles. If you see this, there are gaps in between these grain particles. These are called the porosity. So when these porous features are interconnected with each other, then it is giving a permeability to the aquifer formation. So in the second picture, if you see, the interspaces are filled with further smaller grains. So it will diminish the porous percentage of that rock formation. So this is the primary porosity. For secondary porosity, once the rock is deposited in that environment, when it is subjected to tectonic activities like earthquakes or tectonic movements, then it will generate some fractures or faulting or joints in the rock formation, and when they are interconnected with each other. So here the point is the porous space has to be interconnected to each other, then only it will give a permeable surface, and this is called as the secondary porosity. So geological mapping is another thing which is important for the zonation of recharge area. So in spring shed management, identifying the recharge area is the most common part and the most difficult part. Funding and identifying what kind of structures or interventions you are going to introduce in the area is not that difficult, but finding the recharge zone for that particular spring is very difficult. So for that we have three approaches: catchment approach, hydrogeological approach, and a combination of isotope and catchment, hydrogeology and isotope technique. So catchment is the most layman method to identifying the recharge zone area. We'll just look up from the, suppose spring is occurring here, we'll just consider the upper reach part of that spring as the recharge zone. So here the accuracy is very less. We are not considering the topography, we are not considering anything, rocks or structures underneath. So first is the catchment approach. Second is the hydrogeological approach, where we'll do the geological mapping of a spring shed area. So here we'll identify the rock type, what are the structural controls, like whether it is controlled by fractures or faulting or any linear features. That part will have to do in hydrogeological or geological mapping technique. So in this lecture, I'll be covering mainly the geological hydrogeological technique to recharge zone identification. So it will need you like 2 to 3 days of field investigation, and for that you will need a basic understanding of geology as a whole. So for this you can nominate some para hydrogeologists from that local area. You can take a help from them. And lastly, the isotope technique. I will not go into details about this. Isotope technique, we collect the isotope samples of oxygen 18 and oxygen 18, and we compare it with the rainfall, local water bodies, spring, and with respect to the oceanic concentration of oxygen 18 isotope. So this is a very time consuming process. It will take you at least 3 years, and you have to like establish rain gauges at almost 500 or 1000 meter interval elevation in that slope. So before going to isotope technique, you can use this geological mapping for recharge zone identification. So first geological feature that you have to consider is the rock type. We all know there are 3 kinds of rock types: igneous, sedimentary, and metamorphic. So this is a rock cycles. Once the igneous rock, we all know it is the when molten lavas are like cooling down, it will form a rock formation which is called the igneous rock. So once the igneous rock is formed, from wind and water it will get eroded and it will be deposited in an oceanic or a lake or river environment. Then we will get a sedimentary rock. So again, if this sedimentary rock is further like subjected to pressure and temperature from tectonic activities like plate movements or earthquakes, we will get a metamorphic rock, which is highly it is subjected to highly pressure and temperature. Again, if you further apply temperature and pressure to metamorphic rock, it will again converted into igneous rock. It will again start melting. So again, igneous will convert to sedimentary, or vice versa. So this is a rock cycle, and it is a never-ending process. As I have explained, igneous rocks, when hot lavas are cooling down, it will form igneous rock. So 2 types of igneous rocks are there: plutonic rocks and volcanic rocks. Plutonic rocks are like when magma is trapped inside the earth, it will not come on the surface of the earth, you will get a plutonic rock. And when, as the name suggests, volcanoes, when they erupt, it will come on the surface of the earth, and it will cool very fast, and it will form a very fine grained or glassy texture. So when this volcanic eruption occurs, then you will also see that there are gas particles are also evaporating, like bubbles, hot gas bubbles evaporate from the lava surface, and it will give you a vesicular texture, like small pores you will be there. And when these vesicles or small pores are interconnected with each other, it will form a secondary porosity. So this is an example of a spring occurring in a volcanic area. So volcanic igneous rock terrain in northeastern part is not very common. So this is an example from Maharashtra. So as you can see, these are the vesicles, small nodules. You can see when they are interconnected, it will form a permeability. So in the upper part, we'll have a vesicular basalt with porosity, and underlying which is a massive basalt, because it is trapped underneath the vesicular basalt. The gas bubbles could not escape, so it will not generate any vesicles. So at the contact of these 2 vesicular basalt and massive basalt, we'll get a spring. So this kind of spring is very common in Maharashtra or parts of Gujarat and MP. So in sedimentary rocks, most common type is the sandstone, limestone, and shell. So in sandstones also, it has to be secondary porosity, like it has to be fractured or faulted, then only you will have a porosity, and groundwater can flow through those conduits and occur on the surface as spring. Another sedimentary rock is the limestone. So most common type of spring, you must have all heard about the karst spring, because it is related to the limestones and dolomites. Since limestone and dolomites, they are composed of calcium carbonate, they are highly soluble in water. So when it comes in contact with the rainfall, it will create big sinkholes, and underneath these sinkholes there are conduits which are interconnected, and it will flow as a river underneath the surface and come on the surface as spring. So here is an example of karst spring from Sonmarg. As you can see, these are the sinkholes which is visible on the surface. So these sinkholes are connected underneath and they are feeding to this stream. So this is very common in limestone or dolomitic surfaces. So for metamorphic rocks, most common type we see on the nearby areas is the phyllite, schist, gneiss, quartzite and marble. So this phyllite is mostly common in Nagaland areas, and schist and gneissic, these are common in Shillong part. So when these are metamorphic rocks are subjected to secondary porosity of fracture and faulting, it will conduct groundwater. So as we can see, it seems like a dug well, but it is not a dug well. It is a naturally occurring spring, and these are the fractured gneisses which are giving roots to this groundwater to flow and accumulate here. So here is another example in Guwahati itself. So these are like massive metamorphic rocks, but when they are fractured, it will result in springs. So this is the relationship between the porosity and different rock types. So since volcanic rocks are either vesiculated or fractured, so their porosity will be as high as 50%. On the other hand, in intrusive igneous as well as metamorphic rocks, even if they are fractured, their porosity will be very less. It will be less than 10. So on the other hand, if it is an unconsolidated formation, for example silt and clay, sand and gravel, which we see in the valley areas, for them porosity is very high, up to 70% also it will go. So like that, based on the type of rock type, you can identify the porosity and you can guess in what kind of rock formation you can get a spring. Next is the stratigraphy. This is the relative positioning of strata in respect to geological time scale. So for example, usually when there is a hard rock, it is almost every time it will be overlain by a unconsolidated formation or a loose formation or a fractured formation. So this is the stratigraphy. So mostly in these type of features, contact springs are very common. So this is an example. This, as you can see underneath, if you see, these are very massive, and on the overlying overburden is permeable because these are very loose formations. So water can easily percolate through them, and at the contact you will get a spring. Here is another example as sir has shown in the previous slide. So since Naharlagun is a foothill area, so the upper part of this spring is composed of boulders and cobbles, because this is a Shivalik Himalayas. So they are composed basically of boulders and cobbles, and underlying is the clay particles. Clay, as we all know, they have high porosity, but since their pores are not interconnected, they have very less permeability. Means they will hold the water, but they will not let you drain the water. So at the contact, it will act as an impervious rock. So at the contact we will get the spring. Here is another example. So another thing is the lineament or the linear feature. So if we zoom out on Himalayas in the satellite imagery, it will be viewed as a single line if you zoom out. And another thing is the mid-Atlantic ridge. It is a connection between the it is a crack in the Atlantic Ocean. If you see the satellite imagery, you will get a line feature. So this is the contact zone of two plates. Yes. So we are not going to the large lineaments, but we will be focusing on the more localized linear features like fracture zones, shear zones, or fault alignments. So another linear feature is when there is a fracture in the rock formation, so it will create a weak zone. Along that weak zone, surface water will flow on the surface, and along that weak zone, you will get lots of vegetation, which will give you a linear appearance of a linear feature. So this is a spring in Amingaon. If you see this greenery, it is along the flow direction of the spring. So from this we can say that the flow direction is towards this side, discharge point is here, and recharge zone will be near this bowl shaped like, valley shaped like area. So for that we have to see the satellite imagery, and lineation maps are also available with GSI website that I will show you later. Next is the joint fractures and faults. So, joints and fractures are both discontinuity in a rock formation, but whenever there is a movement along the fracture or the joint, we will call it as fault. So, usually everything appears as fractured, but if there is a movement along that rock formation or along that fracture line, we will call it as fault. So, fractures can be vertical, horizontal, or inclined. So, these directions we will have to measure in the field, because along this direction only, deep and strike of this fault direction will be giving our interventions. What kind of structures what angle we are supposed to construct, everything will be decided by the orientation of these fractures. So, again these are some examples of fracture springs. This is an example of fracture spring in Meghalaya. So, fault spring, as I have explained, if there is a movement along that fracture, then only we will consider is a fault spring. So, identifying a fault in field is really difficult. So, here is a micro faulting in a rock formation. As you can see, this consider the top of this rock block of rock and block of this rock. Previously, it was a horizontal line, like it was connected, but due to some earthquake or some local movement, it must have moved along this fault line. So, this is how fault appears in the field. But it is really difficult to identify fault in the field area, because most of our northeastern region means topography is highly vegetated, and exposure of rocks are very less. So, next geological feature that we will have to consider is the slope. So, slope, when it interacts with the intersect with the local water table, then only spring will be coming on the surface. So, it can appear as a gush of water from like this one, or it can also create a ditch or hole in the surface, and it may appear as a well on the surface. So, like in this slope break, it is intersecting with the water level, and at this point water is emerging on the surface. Another is the ditch and this hole. So, this is an example in Bhangagar, Guwahati. Slope is towards this side. This is the slope, and at the foothill of this slope we are getting a spring here. Again for this one also. This is the slope direction, and this is the discharge point. Again, this is an example of Tripura. Water is flowing from this side. They have a storage tank here, and from here they are collecting the water and distributing downstream. This is an example of depression spring in Karbi Anglong. Actually, this was a video, but it's not playing. As we can see, water is gushing out from this point. So, further they have like created a lake here to collect the water so that they can irrigate the nearby tea garden here. So, to conclude that fracture spring cannot be generative cause cannot be a single factor, like only fracture will generate a spring, or a contact will generate a spring, or it can be a combination of all the things, like it can be a combination of joints, fractures and contact. So, here is an example of volcanic spring in the Maharashtra. So, here the contact of first flow and second flow is also there, fracture is also there, faulting is also there. So, everyone is contributing to this spring. So, mapping in as I have mentioned, it is difficult in northeastern regions because of the high vegetation. So, for that you can use GIS layers which are available in the Bhukosh website of Geological Survey of India. You will get the geology map, lithology map, you will get landslide map also, everything is there. So, you will just need a basic understanding of ArcGIS or QGIS, and from DEM file which is available in ArcGIS, you can get a DEM file, you can generate a hill slope map and drainage pattern of that area. So, for example, I am taking this Saiha Mizoram district. So, this is the geology of the area. As we can see, most of the area is covered by sandstone, and small patches of siltstone and splintery shell are there. So porosity wise, sandstone has highest porosity up to 49% as compared to siltstone and shell. But when you see the lineament or the secondary porosity, you can see mostly secondary porosity is restricted to the sandstone. So further it is increasing the porosity. Already we had the primary porosity of nearly 49%. On top of that, there means due to tectonic activity, we are also getting secondary porosity. So for that, most of the springs which is occurring in the Mizoram district is on the sandstone part, sandstone area. So nearly 78% of the spring which we have mapped, it is in the sandstone area. So another example is from Tripura, North Tripura, Jampui Hills area. So everything is tertiary formation like sand, silt and clay. So porosity is also like more or less same. Entire district is semi-consolidated formation, so porosity is more or less same for all the formation. And if you see the tectonic distribution, as you can see, the district is highly fractured and faulted. These are the fracture and fault lines in the district. But if you see the distribution of spring in the district, only towards the northwestern corner, the alignment of spring is there. Can anyone guess why is it only in the northwestern corner? Okay, because of the slope. Because the slope gradient is only higher towards the northwestern corner. Because groundwater flow always follows the ground surface or the elevation of the surface. If it is horizontal, water flow will be parallel to the ground surface. But as I have said, slope has to intersect with the local groundwater, then only it will manifest on the surface. So only towards the northwestern corner of this district, slope is high. That's why only in the northwestern corner we are getting the spring. So this exercise you can do for an area where you have no knowledge of spring in that area, like totally virgin area, then you can implement this exercise, then you can get an idea ki which direction you should go towards the spring study in a particular area where previous studies are not there. So to recharge how to apply the geological mapping in the recharge area demarcation. So, so previously we have done 6 spring inventory in Kakosang Spring Shed in Karbi Anglong district for Soil and Land Conservation Department of Government of Assam. So under this we have identified these 6 springs. So first of all we have demarcated the watershed of the area. So from there we have studied the geomorphology, slope and geology. So based on geomorphology and slope, we can say that wherever there is a slope break, at the point of slope break we are getting a spring. So if you see the geology, it is composed of mylium granite, which is highly hard rock. So only secondary porosity will be the conduit for these springs. And further, if you see the lineament map, towards the southern part there is a huge shear zone, means it is a highly high fractured zone. So most probably the origin of these springs are from these shear zones. So if you consider a single spring, because the concept of spring is very localized, you cannot consider an entire area for a single spring for recharge. So we suppose this is for a single spring which is Hukan Langso. So this is the spring, just above the spring there is a fracture line. So this is the slope break, like towards this side slope is dipping towards this side, and from here slope is dipping towards this side for this hillock. So and there is a breakage in slope here also. So just above the spring there is a fracture, so we can consider that the area surrounding the fracture will be my recharge zone based on geological mapping. So if you want to make it more accurate, you will have to go for isotope study. So they have implemented, based on these suggestions, they have implemented staggered trenching and some plantations also, and based on that they have improved the discharge of this spring. Another example is from Dima Hasao. This was a project from JJM Assam. So in this spring, which is called as Dima Daupur spring, so they have 2 springs here. One spring here and 2 springs here, but their source is the same. And this is a contact type of spring where underlying rock formation is shell, and the above is the sandstone. At the contact of this sandstone shell, they are getting the spring. So what happens in this area is like this is a spring. They are like consider this spring as very holy spring. So they are not allowing any outsiders or even local bodies to disturb this area. So they are getting water from this spring throughout the year because there is no anthropogenic disturbance in this area. On the other hand, in these two springs, as you can see, there is a huge highway going in this area. So it has disturbed these springs, and now these two springs has dried up. So they have what they have did. Oh, this is the traditional holy spring they consider. So for them, according to the local myth, this water can cure any disease. Like this water is, they are using this for drinking only, not even for washing or bathing, only for drinking purpose. So they are not allowing anyone to enter this spring. That's why I think this spring is still sustaining. On the other hand, in these two springs, what they have done, they have considered the catchment approach, and they have demarcated the recharge zone as just above this springs, the spring 1 and spring 2. They have considered this as the recharge zone. But if you see the geological mapping of the area, so this is the contact of sandstone and this shell, and at this contact the spring is coming out. As we can see, dipping is away from the slope of the area. So if water is falling here, means if we recharge this part, water will flow away from this area, is it not? So for that, if you see, this is an undulating hillock. Like as you can see, it is an undulating hillock. So if we consider this as the contact zone, we have to consider this entire hillock for recharge purpose, because since it is dipping away from the slope, so it must be coming out here as well. So we'll have to consider the entire two hillocks. And if you further see, if you see the anthropogenic activities, there are no major anthropogenic activity in this slope. So this should not have like impacted these two springs. They are going for zoom cultivation in this hillock only. So this is the main reason which is why these two springs are drying up. So for this like dip and strike measurement, we'll have to either use Brunton compass or clinometer. So this is the strike and dip. So either you can use these two instruments, or you can use this map app, Field Move Clino, because these are only available for iOS and Android users also. So while mapping also, it will show you the direction. So with this, you can easily get a clear view where my flow direction will be, which direction I should be focusing on for recharge. With this, I conclude. Thank you. If you have any questions, let me know.